Okay, so let's do some more exercises. One, let V and H be separable Hilbert spaces with inner products respectively, and norms respectively. Let V be have a continuous inclusion in H, the inclusion being dense and compact. Let A from V cross V to R be continuous, symmetric and V-elliptic bilinear form. Let F belong to H. A, there exists a unique U in V such that AUV equals FV H for every V in V. So, this is the immediate consequence of Lax-Milgram lemma. A is a symmetric V-elliptic continuous bilinear form. So, if you look at mod FV, this is less than or equal to norm FH, this inner product in H, norm V in H, which of course is less than C times norm F in H, norm V in V. Therefore, V going to FVH is a continuous linear functional on V. Therefore, by Lax-Milgram, there exists unique U. B, set G of F equal to U, show that G H to H is continuous, self-adjoint and compact. We are of course talking of real Hilbert spaces, that is understood, we are dealing with real functions. Okay. So, this we are trying to imitate what we did for the Laplacian. So, this is the abstract framework. So, U going to F going to U is certainly linear. Alpha times norm U square V is less than or equal to AUU, which is equal to FUH, which we saw is less than C times norm F norm U times V, and therefore you have norm UV is less than or equal to C times C by alpha times norm F, and therefore you have G from H to V is continuous, and this inclusion is continuous and compact. Therefore, G belongs to L of H, bounded linear operator, is compact. It is self-adjoint as we have seen many times. So, we have GF inner product G in H. This is nothing but by the definition GF belongs to V, okay, and therefore this is equal to A of GG GF, which is equal to A of GF GG by symmetry, and therefore that is equal to F GG in H. and therefore G is self-adjoint. So also GFF in H is strictly greater than 0 if F is not equal to 0. So what is GFF? This is equal to A of GG, GF, and therefore this is greater than or equal to alpha times norm GF square. So if GFF equal to 0, if GF equal to 0, then this implies that FV equal to 0 for all V in V, because AUV equals FV, U is 0, therefore this is 0, but then V is dense in H, implies FF equal to 0, implies F equal to 0. Okay. So therefore you have GFF will be strictly bigger than 0 if F is not equal to 0. C, image of G dense in V. You know the G has its image inside V only, and we want to show that it is dense in V. So A is a symmetric elliptic continuous bilinear form. Therefore, UV equals AUV defines an inner product and the norm U of A, which is equal to square root of AUU, is equivalent to usual. So assume V in V such that AUV equal to 0 for all U in the range of G. But U equals G of F, so U equals G of F, and that means FV equal to 0 for all F in H, but V is contained in H, and therefore this means V equal to 0, and that implies that V equal to 0. Okay. So therefore by the Hahn-Banach theorem, range of G is dense in V. Okay. D, there exists an orthonormal basis of H and Wn, because separable Hilbert space orthonormal basis will be countable, and lambda n sequence of positive numbers such that AUNB equals lambda n UNB for every V. So this is the eigenvalue problem, and you can write therefore 0 less than lambda 1 less than or equal to lambda 2, etc., less than or equal to lambda n tending to infinity. So G is H to H compact self-adjoint bounded linear operator. So there exists mu n eigenvalues and mu n goes to 0. Okay, so the sequence of eigenvalues and dimension of eigenspace of mu n is finite. Okay. Now mu n is not equal to 0, because if mu n is, you have g of un equals mu n un, this implies g of un equal to 0, and that implies that un equal to 0, because g of f equal to 0 we know implies f equal to 0, and therefore mu n is not, so mu n cannot be 0, and so we have, and also g of un is strictly positive if un is not 0, and therefore this implies that all the mu n's are strictly positive. Therefore you put lambda n equals 1 by mu n. Okay, so then lambda n tends to infinity, and you have that Vn, un or Wn, okay, I said Wn but I used un, so let me keep it as un. So g of un equals mu n un, that means un equals lambda n g of lambda n un, that means a of un v equals lambda n un v, which is equal to lambda n times un v for every v. So you have the sequence of eigenvalues. Okay, so this proves it. Now you can go ahead and try to show Rayleigh quotient characterization of eigenvalues. So you can write a of r of v not equal to 0, v in v is avv by norm v square h. So this will be the Rayleigh quotient, and try to show that everything will work. Okay, so this way you can study various eigenvalue problems based on this abstract framework. So we will give you one example now. So 2, so eigenvalue problem, Neumann case. So we have done the Dirichlet case in the lectures. So we are now looking at the Neumann problem. So minus Laplacian u equals lambda u in omega, and du by d nu equal to 0 on gamma. Okay, so omega bounded open set, d omega equals gamma. So we will also say connected in this case. Okay. Okay, so now you rewrite this equation as minus Laplacian u equals lambda plus, okay, plus u equals lambda plus 1 u equal to capital lambda u. Okay, so we will write it like that. So we will take auv equals integral u grad u dot grad v on omega plus integral u on omega uv. Okay, and then we take v equals h1 of omega and h to be equal to L2 of omega. Okay, so then all the hypotheses of problem 1 satisfied. So implies there exists an orthonormal basis lambda n Wn of L2 of omega and lambda n positive sequence such that a of u Wn v equals lambda n Wn v. for every v in h1 of omega, and you have lambda n tending to infinity and so on. So, this will imply that grad Wn grad v dx on omega equals lambda n minus 1 integral on omega Wn v for every v in h1 of omega. So, you set lambda n equals lambda n minus 1, and therefore, but then since integral grad Wn dx is greater or equal to 0. So, this implies that lambda n is greater or equal to 0 for all n. Okay. So, what is take lambda, so assume what about lambda equal to 0. So, you have minus Laplacian w equal to 0, dw by d nu equal to 0, this in omega, this in gamma, and w identically equal to constant not equal to 0 is a solution, obviously, and therefore, lambda equal to 0 is an eigenvalue, and this implies that lambda 1 has to be equal to 0. Okay, so this is the first eigenvalue will be 0. And then what is the eigenspace? Suppose you have an eigenfunction for lambda equal to 0. So, minus Laplacian w, what happens is if w is an eigenfunction, w any eigenfunction corresponding to 0, we have that integral grad w square equal to 0, and this implies that w equal to constant. So, eigenspace of lambda 1 equal to 0 is one dimensional consisting of constants. So, we have Wn orthonormal basis for L2 of omega, and then minus Laplacian Wn equals lambda n Wn in omega dWn by d nu equal to 0 on gamma, and you have 0 equals lambda 1, strictly less than lambda 2, less than or equal to lambda 3, and so on, tending to infinity. So, this is the thing, and you can also do the Rayleigh quotient characterization. A. Find the best constant in Poincaré's inequality. When we proved Poincaré's inequality, we got some constant based on the diameter of the set, but so omega in Rn, bounded open set. So, you have mod u 0 omega less than or equal to c times mod u 1 omega for every u in h1 0 of omega. So, what is the best possible constant? So, best constant c implies 1 by c equals inf over u in h1 0 of omega, u not equal to 0, of mod u 1 omega by mod u 0 omega. But we know that if lambda 1 d equals first eigenvalue of delta with u equal to 0 on gamma, that is the Dirichlet boundary condition, okay, then you know that 1 by lambda 1 d is the minimum over all v in h1 0 of omega, v not equal to 0 of mod grad v square on omega by integral on omega mod v square okay, and therefore which is nothing but minimum of mod v square 1 omega by mod v square 0 omega, and therefore this implies best constant C equals 1 by root of lambda 1 d. Equality achieved for u equals w1. So, in any domain, the first eigenvalue of the Dirichlet Laplacian gives you the best constant for the thing. Okay. So, B, find the best constant in Poincare-Wittinger inequality. So, omega contained in Rn bounded, u in h1 of omega, u bar is 1 over mod omega integral omega u, and then mod u minus u bar 0 omega less than or equal to c times mod u 1 omega. Now, if you have this, this can also be written as mod u minus u bar 0 omega less than or equal to c mod u minus u bar 1 omega. And mod u is in h1, then u minus u bar is such that integral u minus u bar equal to 0. Okay. And therefore, you have so Poincare-Wittinger is equivalent to saying mod u 0 omega less than or equal to c times mod u 1 omega, same as in Poincare. For every u in h1 of omega, integral u equal to 0. Okay, so this is the same. So best constant is C implies 1 by C equals inf of mod u 1 omega by mod u 0 omega, u not equal to 0, but integral u equal to 0. But then if you look at the Neumann problem, so you have 0 equals lambda 1 n, which is less than or equal to lambda 2 n less than or equal to etc. So these are the Neumann eigenvalues. So minus Laplacian u equals lambda n u in omega du by d nu equal to 0 on gum. Okay, so these are the Neumann eigenvalues which we saw, and as I told you, you can do the so then lambda 2 n by the variational characterization should be, so you have to check this, so check, okay, will be the minimum of integral grad u square by integral u square on omega, where u is orthogonal to the first eigenfunction. So u orthogonal to V1. So V1 is the space of constant functions equals eigenspace of lambda 1 n, which is equal to 0. Okay, so this is the variational characterization which we saw, and therefore this implies that lambda 2 n is the minimum of overall integral u equal to 0 of mod u square 1 omega by mod u square 0 omega. So best constant in Poincare-Wittinger is C is equal to 1 by root of lambda 2 n, the second Neumann eigenvalue problem. So this way you have that